Alright guys, what's up? Welcome back to C's Get Degrees channel's first ever video. We'll be focusing today on the Catalytic Triad. If you guys know what the Catalytic Triad is, that's awesome. And if you don't know what the Catalytic Triad is, that's also awesome. So before we get right into it, I just wanted to review enzymes, alter the kinetics, and not the thermodynamics. So, just to emphasize, they alter the kinetics, not the thermodynamics. What I mean by that is, say we have a reaction coordinate, so this is energy on our y-axis, and the reaction progression on our x-axis. If we have our starting materials here, and we have, say, an exothermic reaction where we have products here, without an enzyme, it may look something like this. Of course, this is just an estimate. So this is with no enzyme. And say we have an enzyme, so we have a catalysis of some sort, then it may look something like this. So, because it's altering only the kinetics, our activation energy barrier here will be less with our enzyme, but our overall thermodynamics, so our delta G, will stay the same. Awesome. So that's a quick review on enzymes. Catalytic triad is basically
3 amino acids, hence the name triad, that sit in the active site of our enzyme and are responsible for speeding up the reaction.
So, of course, 3 lends itself to the triad and catalysis because it speeds up the reaction. So, some enzymes with the catalytic triad, of course, there's more than one. So, you have chymotrypsin, which we'll be covering in today's video as our example. Another one is trypsin. And a third one is elastase. Here is our example, chymotrypsin, and it's composed of our 3 amino acids here, which is serine, histidine, and aspartate. As we know from our amino acids fundamental knowledge, this is the base of our amino acid, and we could see this in all of our amino acids. So amino acid, so the amino comes from this nitrogen here, and the acid is this carbonyl on the other side. And we know that this part is our R group, so it's our functional group. So each functional group serves some purpose in our catalytic triad. Alright, so this aspartate oxygen is electrophilic for that hydrogen on the nitrogen on our histidine here, and the lone pairs on the other nitrogen of histidine is electrophilic for that H on the oxygen of serine. And what that does is that it makes this oxygen here nucleophilic. So it'll attack something. So the overall reaction of chymotrypsin is to take this peptide bond and break it. So it'll cleave this bond right here. So what it'll do is that it'll produce something that looks like this. And of course, this is just the rest of our amino acids. So what we have here is we have amino acid 1 to amino acid 2, and it'll break that into 2 separate amino acids. So the type of catalysis is called covalent. And I'll show why this is covalent catalysis throughout the rest of this video. So the mechanism. How does the catalytic triad go about breaking the peptide bond between 2 amino acids? And the first step is a nucleophilic attack on the carbonyl. So here we have our serine, histidine, and aspartate. And here we'll form that tug-of-war of hydrogens to form a nucleophilic serine, which will go and attack the carbonyl of our peptide bond over here, and it'll swing the lone pairs onto the oxygen. So the second step is kicking off the second amino acid. So to draw again our network, this is aspartate, histidine, and now you can see serine here. There's a charge on the oxygen that swung up from the previous attack is stabilized by something called an oxyanion hole. So the oxyanion hole of our enzyme stabilizes that negative charge. And we have something called a tetrahedral intermediate here, because this carbon is bonded to 4 different things. So that's 1, 2, 3, and 4. These lone pairs on the oxygen swing down, and it breaks that bond with the second amino acid. So it picks up the hydrogen that's on the nitrogen of histidine. And I just realized this is misspelled. It's okay, this is chemistry, not English. Cool, so now we've kicked off the second amino acid. Moving on to the third step. So here we have water that's going to attack this covalent acyl enzyme intermediate that we have here. So, using what we know about our catalytic triad, how will that go about happening? So, of course, affinity for the hydrogen right there, and then nitrogen's lone pairs will pick up that hydrogen on water to make water nucleophilic, and it'll attack our carbonyl and swing up the lone pairs onto oxygen, giving it an overall negative charge. And now our last step is to reform our catalytic triad and by kicking off the serine. So we have our aspartate here, histidine, and serine. And again, we have, because of water's nucleophilic attack, we have a tetrahedral intermediate again. And this is that oxyanion hole. Stabilize that negative charge on oxygen from our water's nucleophilic attack. And then serine will pick up that hydrogen on histidine to satiate nitrogen's positive charge. And that's it. We have reformed our catalytic triad. We've reformed serine, histidine, and aspartate. So now what does this look like on the reaction coordinate? So if we were to have energy on our y-axis and reaction progression on the x-axis, we have our starting materials, we have our products. We know that we have 2 tetrahedral intermediates, and we have 1 covalent acyl enzyme intermediate. So, if we were to consider these in pink, it would be somewhere right here, and then the other one could be, say, right here. And then purple for a covalent acyl enzyme intermediate would be right there. So the reaction coordinate would look something like this. And there you have it.